So I'm gonna show a use case of Parsl on Elastic Cloud clusters with JupyterLab running on Parallel Works. And I will first quickly introduce the Slurm scheduler-based HPC pools that Matthew was talking about. And then I will start the JupyterLab server on a head node of one of these pools. And finally, I will run a very simple Parsl example with JupyterLab and using the Parsl Slurm provider. So this is the main page of my account in the platform, and you can see that there are different computing resources. You can see 3 pools here in Google, Azure, and AWS. They are all Slurm HPC pools. So basically, the Slurm scheduler has the ability to support a cluster that grows and shrinks on demand, which was originally developed for power savings. And when compute nodes are required, a program provisions the resources from the cloud, then notifies Slurm of their names and addresses, and another program releases them when they are no longer required. So using this capability, we've developed Slurm HPC clusters in Google, AWS, and Azure as pools in Parallel Works. And you can easily configure these pools by going to resources, and then you can click in the pool. This is the one we'll be using today. There are different configuration parameters. You can see my public SSH key, the one corresponding to this desktop, and then some Slurm configuration parameters. For example, the controller machine type. The head node machine type is a C2 standard 8 machine in Google. And you can also define partitions. For example, this compute partition with also a machine type C2 standard 8. You can choose big nodes or nodes with GPUs, and the nice thing is that everything is going to look and feel the same as a Slurm cluster. Each of them has a shared file system, so if you turn off the pool and start it again, these files are persistent. You will be able to access them again, and you can turn on the clusters by clicking on power button. Once this will basically start the head node, and I already started one in the GCP cluster pool. So when the head node starts, the green slider will move to 1, and then as you send jobs to this head node, this is going to request compute nodes, and when the compute nodes are running, they will basically show here as well, and the green slider will move. So basically in this pool, we have up to 10 compute nodes and 1 scheduler node. And the nice thing of this is that you can scale to the cloud with any tool that can talk to a Slurm scheduler, like the Parsl Slurm provider, and you don't need to worry about scaling or staying or developing a provider for every different cloud. And now I'm going to move on to the next part. I'm going to start a JupyterLab server. And to do that, I'm going to use this workflow. This is a Parallel Works workflow. It has an input form with different parameters, so you can start the JupyterLab server on a head node or on a compute node. I'm going to select to start it on the head node. You can choose a temporary password. There is a JupyterLab directory, which is going to be the shared directory that I mentioned. And now you can choose a port number for the server. And then we provide 2 different environments for JupyterLab to run for now. One is Conda, and the other one is Singularity, which is better to run TensorFlow with GPU applications. But in this tutorial, I'm going to use the Conda one. And there's also some description for every workflow. In this case, for now, the user, if they want to connect to the JupyterLab server, they need to start an SSH tunnel. In the future, we plan on better integrating this, but for now, I've added some instructions here on how to do that. I will be doing it in Linux, but you can also do it in Windows with PuTTY. So now I'm going to execute the workflow. You can select which resource to execute it in. I'm going to run it in the AWS cluster. Then I'm going to open one that is already running in Google. So when you execute the workflow, you'll get a new sandbox directory under the jobs directory with the job number. And this has some useful information about how the job is going. So for now, it's waiting for the cluster to start. These are basically a scratchy of directories that you can keep for your records or delete. But I'm going to go to the previous one that I started before. So basically, this is how it looks when the workflow runs. At the end, it has a kind of a helpful command to create the tunnel, although you can do this some other way, but this is there for convenience. So I'm going to run that in my terminal. I can do this because I already added my public SSH key to the resource. And now I can basically just connect to JupyterLab in my browser. I can enter the password. And this should take me to the head node of this cluster, which is basically this IP address here. And you can open a terminal here. And this is a Slurm node, so you can run Slurm commands. You can submit a job with SBatch, and that will start a node for you. And it looks the same in all of the clouds. Then another thing you can do is open a notebook. And these are some sample notebooks that are staged with workflow. I'm going to be showing this one, which is basically it's a very simple scikit-learn clustering example using Parsl, and we're going to train multiple k-means models in parallel, just to show that we can run multiple functions in parallel. So here I'm making the data set, which has 3 features, 3 clusters, and 50,000 samples. So you can plot the data, and it looks like this, with the 3 features that are just called 0, 1, and 2, and the 3 labels. And this is what the Parsl configuration looks like. And the nice thing is that it would look the same in any of the other tools. Basically, I'm using the high throughput executor and a Slurm provider, and I'm choosing to use 4 cores per worker and 4 cores per node. So that's 1 worker per node. And the reason I'm doing this is if you go to resources and you go to the pool that we're using, you see that, as I said, it's a C2 standard 8. So that means it has 8 virtual CPUs, which corresponds to 4 physical CPUs. So that's why I'm using here 4. And then there's 1 node per block. So we're going to scale between 0 and 10 nodes. The Python app is also very simple. It's just takes the data and fits a cluster with the data and specified number of, so it fits the algorithm with the specified number of clusters. Here, scale the data, and I'm going to run 5 jobs with 2, 3, 4, 5, and 6 number of clusters. Here I'm submitting the jobs. So once you submit the jobs, you can see if you go into the terminal and you run SQ that Parsl is requesting 5 compute nodes, and then here I can wait for the results, but I'm not sure if we have time to do this. One thing I wanted to add as well is that another tool, for example, that works in a similar way is Dask. So in Dask, you also have a Slurm cluster object that you can use. And the nice thing of Dask in this machine learning space that I don't see in Parsl, for example, is the compatibility, like direct compatibility with JupyterLab. So you can basically use any scikit-learn model and scale it by just pointing the backend to Dask. I'm not sure if no, it's not finished yet. So because I think I'm already 12 minutes in, maybe we can stop here and 1-2 questions.
Thank you, Alvaro. So I guess just to recap that, I mean, so with a few clicks, you were able to provision a Slurm cluster in the cloud, have your Jupyter notebook there driving things, and be able to run a Parsl-based workflow across the nodes in that cluster. That's a very cool demo. Does anyone have questions on this? I guess one question would be, I know, Matthew, you alluded to this before about how, say, researchers and universities can get on the ParallelWorks platform. Is there like a model where people can jump on and use it sort of at a low cost tier, and then is there a model where campuses are potentially buying into ParallelWorks as a platform? What's the path there for people here who are mostly researchers, I think?
That's exactly right, Kyle. Yes, there's a business model that is very accessible for, you know, kind of individual users or smaller groups, and I think even for research and university collaborators, I think we're very generous there as well, as in we are actively looking for, you know, interesting collaborations, and, you know, we just kind of, we like doing that. So very interested in kind of forming those collaborations for larger deployments like the NOAA one we did. There's kind of different sets of licensing models that as you increase the number of, they're mostly all user seats. So as you increase seats, the cost per seat goes down per year. That's the summary, I'd say.
So if you want to run parallel things on the cloud, this is probably a good way of doing it, because probably the savings costs that you guys would provide would make up for that delta. Any other questions from people in the audience around ParallelWorks and the demos we just saw?
I have a quick one. So there is a lot of emphasis on like the cluster software, like the cluster providers for connecting and like spinning up clusters on the cloud. Is that primarily because there is a lot of like MPI applications that your user base has, that, you know, that they would rather use a cluster, a more MPI friendly interface rather than, like, say, something like Kubernetes? Or do you see like a shift there?
Yeah, I guess, again, being customer driven, you know, our task from NOAA specifically was to emulate their on-prem environment as closely as possible, like from the file system level and everything. So we emulated that, you know, initially now, where they're using Slurm with a Lustre file system on premise on all their different systems. We just replicated that over here. So for those 1,000 users or so that are in their RDHPC group, very easy transition. They don't have to like restructure things too much other than build their software in cloud. So that was the primary motivation there, but, you know, and they're heavy MPI as well. So, I mean, their jobs typically, you know, 4,000 cores or so is what I'd say the mean is of what they're running. So like their production ones, or some of their production, each member, I guess. So yeah, that's the point there. I think our vision is to start supporting many different scheduler fabrics, including, you know, Kubernetes clusters in the same type of, you know, easy way of provisioning.